long mathematical induction proofs before we leave. And the proof goes like this. Here's the claim. So the claim is, what's a good claim color? The claim is, just want to get this right. Where did I write it down? There we go. Actually, the claim's about this recurrence. So I'm going to define a sequence. So the sequence is going to go like this. We're going to have A0 equals 1 and A1 equals 0. So we have two base cases for our recursive case. And then we're going to have AI is going to equal AI minus 1 plus AI minus 2. Actually, I'm sorry. I wanted to have 1 and 2 here. There we go. AI minus 1 plus AI minus 2 plus I for all I greater than or equal to 2. So here is the sequence. And then my claim about this sequence is that for all I greater than or equal to, for all I in the set of integers such that x is greater than or equal to 0. So for all integers greater than or equal to 0, AI is even, I is even, and AI is odd, or I is odd and AI is even. So just saying that I will be the opposite of AI. The index will be the opposite of whatever the actual thing is. That's the weird claim about this weird set of things. And let's just look at a couple, right? I mean, A0 equals 1. 0 is even, 1's odd. That checks out. A1 equals 1. Or sorry, A1 equals 2. 1 is odd, 2 is even. That checks out. A3 is the first interesting one. This is going to be, so the way you make the next terms in the sequence is you add the two previous terms and you add the index. So here the two previous terms are going to be 1 plus 2 plus the index is 3. So 1 plus 2 is 3, 3 plus 3 is 6. 3 is odd, 6 is even. A4, we're going to add the two, oh, I'm sorry, wait a minute. Sorry, man. We add the two previous terms and we add the index of 2. So we get 2 plus 2 is 1, we get 5. So 2 is even, 5 is odd. A3, we add the two previous 2, we get A1 plus A2 plus 3, which is A1 is 2, plus A2 is 5, plus 3. That's 7 plus 3, which equals 10. So again, odd, even. So it looks like this always works. And why would this always work? Well, this seems to always work because notice that every two consecutive numbers, like these two, these two, these two, are going to have opposite parity. So 1 and 2, 1's even, 1's odd. 2 and 5, 1's even, 1 odd. 5 and 10, 1's even, 1's odd. So when we go to calculate an plus 1, which equals an plus an minus 1 plus n plus 1, an plus an minus 1 is going to be odd. There's going to be an odd plus an even or an even plus an odd. They're going to be opposites at the point. It's going to be odd. And then an odd plus an even is an odd, and an odd plus an odd is an even. So AN is going to be the opposite of whatever n plus 1 is, which is exactly what we wanted to show. We wanted to show they'd be opposites. So if n plus 1 is even, the whole thing's even. If n plus 1 is odd, the whole thing is odd. So assuming that AN and AN minus 1 work in the sense that they'll have opposite parities of their indexes in n minus 1, well, then we know it's going to work for n plus 1. And that's the chain reaction. That's the induction. So I'm going to prove it real quick. Proof. Proof by strong mathematical induction. We're actually going to skip the base case and come back to it because it's a little interesting. Let's do the inductive step. So here the inductive step, we want to show that for all n greater than or equal to, I'm going to say 2. P of 0 all the way out to P of n implies P of n plus 1. Why do I start at P of 0? Well, because remember, we want to show this for all integers greater than or equal to 0. So we want this to be true for all integers greater than or equal to 0. So in the base case, we're going to want to show P of 0 is true. Here's the thing. We're also going to want to show P of 1 is true. And you'll see that in a second once we do this argument. So let's do this argument first. So I want to show for all n greater than or equal to 2, P of 0, P of n implies P of n plus 1. i.e., we want to show that for all n greater than or equal to 2, for all n greater than or equal to 2, actually, we're using I here, so I use I. So I want to show for all I greater than or equal to 2, if k is even and ak is odd, or k is odd and ak even for all 0 less than or equal to I, k less than or equal to I, then n plus 1 is even, or then I plus 1 is even and a of I plus 1 is odd, or I plus 1 is odd and a of I plus 1 is even. This sounds really complicated. Let's just write down the claim. All we're trying to say here is that for every integer, we want to show that for any I greater than or equal to 2, if we can show that the claim is true for everything between 0 and I, then it'll be true for I plus 1. That's the induction, because then once you have that, you can prove the next one, the next one, the next one. So here's how we're going to do that. Let I be greater than or equal to 2. Let I be an integer such that I is going to equal 2. Then I'll say consider a of I plus 1. A of I plus 1. So notice that since I is greater than or equal to 2, actually, I'm going to use 1 here. Let's see why in a second. I could use 2, I'm going to use 1. Since I is greater than or equal to 1, I plus 1 is greater than or equal to 2. Why is that important? That's important because by our definition here, since I plus 1 is greater than or equal to 2, we can use this formula to compute AI plus 1. So, thus AI plus 1, because I plus 1 is greater than or equal to 2, we can use it here to show it's the 2 previous. There's going to be AI plus 1 minus 1 plus AI plus 1 minus 2 plus the index, which in this case, AI plus 1 minus 1 is just AI. AI plus 1 minus 2 is AI minus 1 plus I plus 1. So here's the key. The key is because I is bigger than or equal to 1, I plus 1 is bigger than or equal to 2, so we can calculate it using our recursive formula right here. And by our assumption, AI and AI minus 1 kind of follow our claim, meaning if AI is even, AI or I will be odd. Oh, sorry. If I is even, AI will be odd. If I is odd, AI will be even. And same thing with AI minus 1. Note by previous results, I is even or odd. So now I have 2 cases. Case 1, assume I is even. Then, since uh, 0 is equal to I less equal to I, by our assumption here, where we want to assume that P of 0 all the way up to P of I is true, by this assumption, AI is the opposite parity of I, thus AI is I. So since I is even, and we're assuming this claim holds, or assuming this claim right here holds for all I, for everything between 0 and I, that means that AI must be odd. Further, since I is even, I minus 1 is I. You've shown things like that before. Then because 0, because I is greater than or equal to 1, I minus 1 is equal to 0. Hence, 0 is less than or equal to I minus 1, which is less than or equal to I. Why is that important? Because again, we see that for everything between 0 and I, our claim up here is true, that the parity of AI would be the opposite of A, or opposite of the index. Thus, by our assumption, AI minus 1 has the opposite parity to I minus 1. Hence, AI minus 1 is I minus 1 was odd. Hence, A minus 1 is even. Hence, AI minus 1 is odd. So all we've shown is in the case where I'm way over. Sorry, people. Anyone can leave whatever they want. I'm going to trim this video down and put it online. It's going to be about an hour. And yeah, but anyway, so the point is, so A minus 1 is the opposite parity to I minus 1. Hence, A minus 1 is even, since I minus 1 is odd. Thus, AI plus AI minus 1 is odd because an even plus an odd is odd. So we've shown that if I is even, AI will be odd, and AI minus 1 will be even. So AI plus AI minus 1 is odd. Finally, since I is even, I plus 1 is odd. Thus, AI plus 1, which equals AI, is AI is I minus 1 plus AI, will be an odd plus an odd will be even. It is an odd AI plus AI minus 1 plus an odd I plus 1. So, this might have seemed kind of complicated, but here is the point. The point is, assuming I is even, and knowing that I is greater than or equal to 1, knowing those two things is enough to know that I plus 1 will be odd, and AI plus 1 will be even. So they have their opposites like we wanted. And if we assume AI is odd, we can use basically the exact same proof to show that the exact opposite happens. If AI is odd, then I plus 1 will be even, and AI plus 1 will turn out to be odd. The point being, that assuming that I is greater than or equal to 1, we can assume that I is greater than or equal to 1, and assuming that the claim is true for 0 all the way out to I, we can show P of I plus 1 is true. We can show that the index and the term have to be opposite for I plus 1. AI plus 1 and I plus 1 have opposite parities. And so what I'm going to do is I'm going to just erase this. That's okay. And I'm going to say we're going to have a case 2. I is odd. And by same logic, we can show up right at time. By same logic, I plus 1 will be even, and AI plus 1 odd. Thus, in either case, I plus 1 is even, AI plus 1 is odd. Thus, in either case, AI is even, AI plus 1 is even, and I plus 1 odd, or AI plus 1 is odd, and I plus 1 even. Conclusion. Therefore, for all n greater than or equal to 0, or for all I greater than or equal to 0, I and AI have opposite parity. Meaning one's even and one's odd, or the other, or the first one's even and the next one's odd, or the first one's odd and the next one's even. So that was a very long and very convoluted kind of proof of even and odds, but here was the big point. The point is that once I is bigger than or equal to 1, once we know this, we know I plus 1 is bigger than or equal to 2. And if I plus 1 is bigger than or equal to 2, all of a sudden we can use this recursive definition to talk about AI plus 1. That's the key. I plus 1 greater than or equal to 2 means we can use this formula to calculate AI plus 1. And then using this formula was the key because we had this, and using this formula was the key to show that, oh, okay, it holding for the previous ones will prove it holds for AI plus 1. But we had to start at 1 because we needed to use this formula to do it. And so since we needed to use this formula to do it, we actually just need to show that it works for 0 and it works for 1 just by brute force, because we don't have a clever way to do it because they're just kind of like defined. So that's why we need to show the base case for 0 and 1, and then we start at 1. So we want to show P of 0, and P of 0, we can do that just by saying note 1 is, or 0 is even, and A0 equals 1 is odd. And here we can note 1 is odd. And A1 equals 2 is even. So sometimes in strong induction, you're going to have more than one base case. It just depends on when this chain reaction takes over. This chain reaction takes over once I is bigger than or equal to 1. So that means that to prove 2 is the first way we can prove using the chain reaction. So that means we have to show 0 and 1 by brute force. But I am way over. I'm going to write up this proof all nice and put it online. And I'm going to put out some extra examples if you guys want them too. So does anyone have any questions?
You wanted me to talk to me about stuff, or the?
Yeah, we'll do that. We'll do that in a second, Alex.
Yeah.
All right, no any questions. Sorry for going over, but this has been a great class. I wanted to get this down because I wanted you guys to be able to do your homework. So sorry about that. But like my announcement says, we will have class Monday. We'll be going over a bunch of reviews on this stuff. And then Tuesday, no class. Good luck on the test. No homework next week. So we're going to chill. So sorry for going over, but enjoy your no class day while you're taking the test.
Thank you.